Perfect. Thanks for coming for my talk today. May I introduce you myself? My name is Bernhard Scholz. I used to work for the University of Sydney for many years, but took leave recently, roughly 1.5 years ago, to become the Chief Research Officer of Fantom. And what I want to present today is really the work we have been doing recently. And it's Fantom's new technology, the new technological stack of Fantom, which we call Sonic. And just in case you don't know, Fantom is an L1 blockchain. So the idea here is that we have an EVM-compatible blockchain, which is permissionless, and it allows to really execute smart contracts. So it's programmable, similar to Ethereum, and it can execute Ethereum smart contracts. The idea of Fantom is really that we want to innovate the space. So we believe strongly in innovation, in making the field as interesting and as inviting as possible for society to really deploy applications which matter. And for this, we need a lot of innovation. And we believe that L1 chains, so chains which do not rely on upper layers which go on top, like L2s and so on, we believe we can do this all in the L1, and for this we need a lot of innovation to make it as fast and as responsive as possible. As I said before, we really believe in innovation, and it's not just a marketing work innovation. So here what we're doing is really, we thought deeply how we can innovate the company as quickly as possible. And so when I left the university, what I did was I actively was looking for talent. And how I did this, I really searched for industrial researchers, for people who have PhDs in computer science. And with those folks, we sort of tried to ramp up the innovation in Fantom. And the idea here was to really place them in our engineering teams. And with the engineers, we developed this new technological stack of Fantom, which makes Fantom really super competitive, super fast in the L1 chain world. The reason why we need industrial researchers with PhDs is quite obvious, because L1s have a lot to do with databases. We have something called the world state, sort of a state of accounts and balances. And for this, we need database technology to store the world state. So you need really database researchers to really fully understand what's going on and how to improve these sort of storage problems in L1 chains. We have, at the same time, also programming language problems. So we need people who have really deep understanding of programming languages, researchers. We have other issues like distributed systems for consensus and operating system aspects. So we need really very deep knowledge in computer science to innovate. And so our idea was really to place these researchers into these engineering teams, and with them, we could really advance the technology very substantially, which I will present later in terms of transactions per second, time to finality, and all this. So the focus of Fantom is really building a network of value. And our sort of approach for this is really to have an efficient use of resources. By making resources as efficient as possible, in our case, computers running the blockchain, we really think that with this approach, we can make the transactions and the network much cheaper to operate. And with these ideas, we had to change also our approach, how to do the engineering for the L1 chain. So we gave this approach even a name. We called this performance engineering. And what it is really is we take the L1 chain apart into its pieces and then try to figure out what each of these individual parts is doing by carefully measuring these parts and analyzing what's going on. And through the performance analysis, we identify bottlenecks, and in the next step, we iterate again and again to eliminate the performance bottleneck, and then the analysis and the identification of the bottleneck starts again. And with this performance engineering approach, we could really improve the use of resources, and this manifests in very high transactions per second and a very short time to finality. So we really put effort into making this approach as efficient as possible to make the L1 chain as cheap as possible to run. But the nice side effect is also we use much less energy for doing all this work. So what we have achieved is really, with this new technological stack, speed. So with this new approach in terms of innovating and using industrial academics, we could really push the L1 to its limits in terms of speed. We have also really nice scalability because we improved the consensus, and we have really nice security because we don't rely on L2s and other higher levels of blockchains operating on our L1 chain. So we really achieved this with our new technological stack, and this is what we have been investing. But the interesting part here is when we want to really make this technology available on the mainnet next year, we will have a lot of supply. And with that, of course, we are very interested in builders, and if you have interest running dApps on the L1 chain, please have a look on our web pages. We have programs like the gas monetization, where we really support dApp builders to make use of this very fast, very effective chain in future. So let me introduce you now really the results of Sonic. This is really an achievement because normally L1 chains are very slow, and the time to really settle a transaction can take in other chains minutes or hours. But our approach, our consensus algorithm, and our fast block processing really allows to push L1s to the limit, and we achieved a throughput of 2,000 transactions per second. So this is really remarkable for a L1 chain. And similar, we have something called time to finality, which is really the time it takes to issue a transaction and to see it manifesting on the blockchain. So we have a time to finality around 1.1 second. And the average block rate is really below a second. So this is really the rate it takes, it has producing a new block. This kind of results, this is a testnet. It's not the mainnet. This will follow next year. But with that, we really have a very fast chain. We get this is now really metrics about smart contracts and how fast they execute, but we get roughly 430 million gas per second. This is sort of the complexity of smart contracts measured. And the other big important thing, which was really where we were struggling with, was the disk usage. So we used Ethereum's MPT data structure. I don't want to be too technical today, but a data structure from Ethereum, and that consumed a lot of disk space. And with that, we had issues running validator nodes, running the nodes of the network effectively. And with this new technology, we could substantially reduce the disk consumption to roughly 160 gigabyte per 100 million transactions for around 9.3 million accounts. So this is really mimicking roughly the mainnet. So we wanted really not to have here a demonstrator which is totally off from the mainnet. We really wanted to have it as close to the mainnet as possible to really see how our new technology will react in the next year when we deploy it on the mainnet. So what this really means is suddenly we have really this vast volume of transaction we can process a day. So the management, when I started, said to me, well, we want to aim for 100 million transactions per day. And you can ask, why 100 million? And the reason for this is really that 100 million is sort of the volume of transactions of Visa in a single day in the United States. So it was at least a few years back. And we could really exceed the expectations of the management by providing a technology which can even do better than what Visa processes in a single day in America, by really achieving roughly 7.2 million transactions an hour, or even hundreds of 200 or 300 million transactions per day. So this is really a vast amount of transactions which can be processed. And you can imagine that with this vast number of transactions, storage will become a serious problem, because these transactions and the changes of these transactions to the world state, to the balances, accounts, need to be, of course, stored somewhere. And so you can see that on one side, the transaction speed is important, but on the other side, we also need storage capabilities for taking care of this huge number of transactions. So you can ask, well, what are the insights? What made these things so fast? And first of all, to make the processing so fast, we really invested a lot of time and effort making the virtual machine of Fantom super fast. And this started way back even at the university, working on new techniques to really make the smart contract execution very efficient. And we needed to use very specific techniques which were invented for binary translation. So this is really when, for example, Apple moved from Power PCs to Intel PCs. They needed very specific translation techniques, and Fantom Virtual Machine uses very similar techniques to make the execution of smart contracts fast. Then, of course, we needed a new database. So that was also a significant effort building this database. And that was key for Fantom's speed. And the last thing, we needed to make changes for the distributed system to have it process these vast number of transactions through the network as quickly as possible. So what I want to do now, a little bit drill down to the technology itself. So the Fantom Virtual Machine is based on something called dynamic translation. And we were not initially too happy with the Ethereum virtual machine, but we wanted to have full compatibility. And the reason is that the EVM virtual machine may not be fast enough for applications where you want to drive an L1 chain up to 2,000 transactions per second. So we needed really better block processing technology. And so we came up with this idea that, well, we needed a faster virtual machine, and this needed a complete new architecture, but we couldn't really afford building a new virtual machine standalone. We needed some technique which allows us to use the EVM code base and the programs running on EVM seamlessly on the new L1 chain. And so the idea here is really that in the client, so this is really the software which runs the network. In that client, we have something called a converter, and it takes the EVM code of the smart contract and translates it on the fly to a new sort of virtual machine format. Mind you, this is called the Fantom Virtual Machine. We had internal project names. We called these whole virtual machine project Tosca. We had several virtual machines. This is sort of one of them which really won the race. And this dynamic translation to this new virtual machine allows us to use a much better encoding. We use something called super instructions, where we have a couple of instructions put together to a super instruction. This kind of formatting of the virtual machine code allows then a much more efficient execution, because certain patterns which show up very frequently can be executed with much more speed. But there are other goodies like jump test analysis, which ensures that jump destinations are correct, can be performed much more efficient than in the EVM, in the original EVM. So there are a lot of very technical details in the Tosca virtual machine or Fantom virtual machine, which allows us really to execute substantially faster than the original Ethereum virtual machine. As I said before, storage was equally an important issue. So we needed much more advanced techniques to store the world state, to store the balances, the smart contracts, and so on. And what we saw is that there were two use cases. One is the LiveDB use case, the other one is the ArchiveDB use case. So the LiveDB is really just what's going on currently in the blockchain, what is the latest block doing. And the ArchiveDB is related to sort of, you can say it's the librarian, it's the historical transactions which are accumulated there. And for this purpose, we needed, we made the decision to split the functionality between LiveDB and ArchiveDB to make things really fast, depending on the use case. Whereas traditionally, there would be only a single database. We have very special techniques to get cryptographic hashes for the LiveDB. We have verification for ArchiveDB. And the other interesting technical detail here is that we have a native database. So these databases really write to file rather than going through a key value store through another database, you can say. So these kind of changes were really fundamental to make block processing super fast. So just more to the setup. So we have this kind of setup of 21 nodes in the Sonic testnet. I can show you for more numbers and the web pages to get access to this. These are quite sort of decent nodes, Ryzen 9 with 128 gigabytes. But in future, you can say with this new technology, you can run the current performance really in smaller nodes. Then here for the testnet, we have sort of a workload of 65% of ERC20 contracts, 25% swap trades, 1% Uniswap, and 10% wallet transfers. This sort of mimicking, again, our mainnet on Fantom for the blocks between 0 and 65 million. Here, just really a results table. The original mainnet couldn't process more than roughly 30 transactions per second. The new one can really do 2,000, so you can say it's 65 times more. The actual block processing without the distributed system and all this of mainnet was around 500. So this is really the speed of the virtual machine and the database. And the new one can do 4,500. So gigantic improvements. And storage, again, from roughly 11 gigabyte, or you can say 11,000 gigabyte or 11 terabytes down to roughly 1 terabyte. Synchronization could be improved substantially from nearly a month to 2 days. Another big problem was pruning. So this is really to get rid of history in validators. So that was really the reason why we needed the LiveDB, to make that as efficient as possible. Validators needed offline pruning, so we needed to stop these nodes and then run pruning, getting rid of historical state. And with this new technology, there is no need for stopping nodes for 30 minutes, doing the pruning, which may take 3 to 8 hours. And so this new technology will really simplify substantially the use of the hardware and would not disrupt validators to earn money. And this pruning operation is quite an operational risk as well. So if something goes wrong, validators may lose quite a bit of money. So here, just an overview of these advantages of the new technology. So we have, again, 65 times roughly and speed up in throughput. We have very low time to finality. We have live pruning to make the life of validators better, and it really improves the robustness of the network. We have very low synchronization times, so when we need to start a new validator, and we have very low storage requirements. Please have a look. We have here the link for the Sonic network. Have a look, see it how it's working. We have a closed Sonic where the network is really driven to the limits. So a transaction feeder pushes in synthetic transactions, and there's no space for public interaction because all this performance is used up by the transaction feeder. But it really shows the performance of the network. So these are not paper numbers, these are real numbers. So there's a real network running, and there's a simple browser, a simple explorer showing these numbers. So you can really see the sheer performance of this new technology. And there's an open one where there's still a transaction feeder, but with much less transactions per second. It's roughly 100, and you can interact with that. So you have sort of options to interact via MetaMask, or there's a simple wallet on the internet. You can issue tokens via faucets, issue transfers, trade ERC tokens, And there are also some instructions how to deploy your DApps. So what's the roadmap now? So the Sonic demo and the technology is already out. So please go to our web pages and check out, play with it, give us feedback about it. Next year, sort of in Q1, so from the period of January to March, April, we really want to deploy this new technology on the mainnet. Over the year, we will have some performance upgrades. Later in the year, we will further improve the consensus, sort of the distributed system aspects of the system. And then for the year after, we plan to do horizontal scaling, making things even more efficient than what we have it at the moment. Thanks so much for your attention.